Swayam Prabha. Digital India. Educated India.
Yeah, welcome back. So, we will start from tests that are done for transformers, the open circuit and the short circuit tests. So, the point is that any equipment when you buy or you manufacture, there is a requirement to measure the parameters of the transformer. Otherwise, how will you model that transformer in some other studies? It is a part of a bigger chain, right. I mean, for example, as a transformer is a part of a distribution system, transformer is a part of your residential supply, it is a part of a distribution system, it is part of a transmission system and so on and so forth. And then there are transmission lines, induction machines, generators, and we are studying many times equipment, the performance of equipment in particular, and we are sometimes testing the performance of the grid. So, both of these parts should come out properly, and therefore, we need to know the transformer parameters, what is the leakage reactance of the transformer. We also want to know the efficiency during operation, we want to know the voltage regulation, that is when we connect supply close to primary to close to nominal voltage, whether the secondary voltage will be close to nominal or not. Otherwise, the equipment which is connected there as load will not function satisfactorily. So, all this means that we need to know transformer parameters and losses. Losses for efficiency, two losses, copper losses and copper losses or I square R losses, and iron losses, that is hysteresis losses and eddy current losses. So, these are the lossy elements which will whose values will determine the efficiency that we are going to get from the transformer. And we also need to know the impedances, the net impedance of the primary plus secondary winding, usually that is something which is very important to know for the purpose of calculating the voltage regulation. Like if I connect so and so load to the secondary and primary is supplied from the rated value, what will be the voltage developed on the secondary. So, this is a question, and what is the voltage regulation? Is it like 1%, 2%, 3% which is acceptable, or is it like 10% which is unacceptably high? Because if you for example, connect it to a 400 volt supply and you lose 40 volts or gain 40 volts, that is your voltage becomes 440 or 360, then that is not an acceptable drop, that is too much of a drop in the voltage. So, for all this we need transformer parameters and their losses, open circuit losses, I mean the iron losses and the copper losses at full load, and from there on we can predict how this transformer will perform given a certain set of operating conditions and load. So, let us start with there are two tests to measure transformer parameters. One is known as the open circuit test and other is known as the short circuit test. Open circuit test is usually used to measure, to calculate main thing that this test does is gives the core loss, which is basically also sometimes called as iron loss, because iron is the predominant element in the core. Also, that is, it gives you sum of hysteresis loss plus eddy current loss at rated voltages, because you usually connect a device to a rated voltage, right? I mean, you look all around you, the voltage is close to nominal. That is a requirement, plus minus 5% of the nominal voltage value. So, you want to know what is the core loss at this voltage excitation level. So, that is what we are going to calculate, and you will also get no load current. This is also important, is it not? The no load current is important because you want to make sure that it is not like more than 5%, it is just a couple of percentage of the full load current. Otherwise, you have got a transformer which is not a good piece, it is drawing too much of current under no load conditions. Ideally, no load current should be as close to 0 as possible, but that is not going to happen. But a 100 voltage ampere device, suppose it is taking up to 1 ampere, you will say very happy, up to 5 ampere, okay. Afterwards, you will start like saying, what is this? I have not connected any load to this circuit, and yet it is drawing so much of current. This does not make sense, right? So, the no load current also you want to measure, and once you know the losses, suppose you know the losses and you know the voltage which you have connected and the current that it is carrying under this thing, then obviously a derivative thing is you will know power factor at no load. So, you will know the power factor at no load. If you know power factor, needless to say that you can also calculate Rm and Xm. No load current is usually shown as this. These are some of the things that will come out of the open circuit test. From the short circuit test, you will mainly get the voltage drop in the transformer during rated conditions. That is, you have connected full load at some power factor to the volt ampere load at some power factor to the secondary, and excited the primary using the normal rated voltage, and then how much is the voltage which is dropping. This you will get a measurement of that. You will also, because you will measure again voltage, current. So, therefore, you will also come to know and once you have measured the power, you will also come to know the power factor at the short circuit. You will also come to know, we will call this as VSC, phi SC, and you will also come to know power loss, which is I would rather call it copper loss, but we will come to this. You will measure loss using wattmeter, is it not? So, you will come to know the loss, which in this case is a copper loss. I will explain that under rated condition. So, from these two tests, the OC test plus OC test plus the SC test, you can evaluate using pen and paper the performance of the transformer under various operating conditions. So, every time you do not need to do tests, you do these two tests and done. Then you say half of the load transformer, what is the efficiency? Here I will give you the value. What is the voltage regulation? This is what I will do. Power factor has changed, I want to know how my transformer will perform. Here is my pen and paper calculation and the answers come out. So, that is the advantage of doing these tests and developing equivalent circuits. Every time you do not have to run around doing this test, they setting up the test, needing the space, equipment, and in field how can you do it? It is doing its job. You cannot like stop it and take it out for doing some tests and then connect it back. And if you connect it, do not do this test and then connect it and it does not give you the right kind of a performance, then you are going to have some kind of a problem, is it not? So, therefore, it boils down to saying that these tests are important tests. Let me start with the open circuit test. In the open circuit test, what I do is I take the primary. So, this is my transformer. Let me start from here. This is my transformer. This is the primary, this is the secondary. Now, the secondary is going to be kept at open circuited. That is why this name of the test is primary. And I am going to connect the supply, I am going to connect the rated voltage at rated frequency to the primary, but I should put instruments, right. I mean, I should put instruments to measure everything. So, I should connect an ammeter and a wattmeter, and I should also connect a wattmeter. This is usually said to be the current coil of the wattmeter, and this is the said to be the voltage coil of the wattmeter, because the wattmeter to calculate power needs both voltage and current. You know, VI cos phi is the power in the sinusoidal circuits. These are my connections, and so this I can mark it as W, and I should measure the V1 and I should measure the V2 of the transformer. So, this much is the instrumentation which is required: 2 voltmeters, 1 ammeter, 1 wattmeter. Now, what you will do is, so you will measure V1. See, secondary is open circuited. If this current is, even if you take 5%, it should be probably less than the 5%, but even if you take that the no load current is approximately 5% of the rated value, the voltage drop which is going to happen in this is going to be very small, and the voltage drop is actually in the two parts. One is the wire which is connecting to your supply, which is negligible, and whatever is taking place inside of this transformer, which is due to the leakage, primary leakage reactance, primary winding resistance, and the core losses, the magnetizing impedance. So all that put together is going to come here. If you want to recall your circuit, equivalent circuit, this is RM, this is JXM, this is the one, I am sorry. So, this is open circuited, this is connected to supply, and when I measure the voltage at the terminals here, basically I am going to measure this V1, this V1, and when I have connected the voltmeter on the secondary side, then I am measuring this V2. So, clearly V1 to V1 by V2 is basically approximately equal to N1 by N2. The reason is of course that I am sorry, the correct way to show this would have been that nothing wrong, I could have put a dash there, but what I wanted to say was, the point which I wanted to convey was that here is an ideal transformer, and then here is the R2 and JX1, JX2, and this is what is V2. So, the turns ratio is, if you call this as E1, the turns ratio is actually E1 by V2 is equal to N1 by E2, but because the voltage drop here is less than 5%, node load current is less than 5%. So, the voltage drop is also going to be less than 5%. So, therefore, it can be ignored in with respect to this, and so this is approximately equal to V1 by V2. Even we cannot measure this. This is a part of the transformer, this distributed part of the transformer. In equivalent circuit, we are showing it as lumped thing, but it is not really something that is lumped. So, we are measuring V1 by V2, but because the current is only I naught is less than 5%. So, therefore, this approximation is a good approximation, and from here you can actually check the turns ratio of the transformer. You will not know actual number of turns, that is manufacturer specific thing, he will not give it to you, you will not know that value, but you know the ratio of V1 is to V2 is approximately equal to N1 by N2. So, one part is in fact, I had not listed it here, but open circuit test gives core loss, iron loss A, B, C, D, and I will add E also, which is ratio, turns ratio. N1 is to N2. Okay. Now, you measure, you apply rated voltage to the primary. Now, actually sometimes suppose you have a big transformer, means like turns ratio is say 1 is to 1000. Now, what is easy to get a 1 volt supply or a 1000 volt supply? Many times it is easy to get a 1 volt supply rather than a 1000 volt supply, which will be much more bulky and so on and so forth. So, in that case you can, for the purpose of doing this test, treat the low voltage side as the primary and connect it to there. This is just to improve this is just to make your instrumentation sort of connections, instrumentation, supply sources, looking to that you may decide to do that you will take primary to be the low voltage side, because low voltage supplies are much more easy to get than the corresponding high voltage side. But what I am trying to say is, you main thing is you should keep one side open circuited and another side you should connect a rated voltage source. Which side you use, it depends upon your choice of availability of the voltage supplies and so on. Suppose you have voltage supplies for corresponding to rated primary and rated voltage, then you choose primary only and connect the primary side rated voltage only and connect rated voltage to that primary side. Okay. Now, suppose whatever loss that I have measured here, this loss I am going to call it as the open circuit loss POC. So, POC is measured by what? This wattmeter, and I naught is measured by what? This one, and rated voltage you are going to apply here. See, these current coils and these coils have very small impedances. So, this can be ignored. So, this rated voltage is also essentially measured by V1 only. I do not need to connect another V1 here. These drops are negligible. This ammeters and wattmeters, basically current coils and the voltage coils and their requirements, we have discussed it earlier. So, this POC is practically measured in watts, is practically constant, and you can also say that Vm square by Rm plus R1, which is approximately equal to V1 square by Rm only, is because this drop in this resistance is negligible in comparison to Rm. So, therefore, this V1 square by Rm is approximately equal to this POC, from which you can get the Rm value. So, you can calculate the Rm value from here. Now, if you look at V1 by IOC, the open current value, then that is nothing but, or if you want, you can take the other way round. If you look at IOC by V1 magnitude, then that is nothing but the magnitude of G plus JB, the G plus JB part, where G is GM plus BM, if you want to write that, where GM corresponds to 1 by Rm, which you have already calculated. So, this is nothing but under root of GM square plus BM square, and these currents and voltages are measured. You already know this BM Rm value. So, you already know this GM value. So, now calculate BM, or in other words 1 by Xm, or in other words the 1 by Xm value from here. So, you can actually calculate these values from the open circuit test. Now, let us come to the short circuit test. So, in the short circuit test, basically what we are going to do is connect a low voltage supply to the primary. I will explain why I say why I say. Let me start first by again drawing my primary and the secondary, and I need a variable voltage source here, because VSC, which I am going to connect through again an ammeter, a wattmeter, a wattmeter, and a voltmeter, which is to measure what is I have connected here, and the secondary is going to be short circuited. So, that is why this test is called as the short circuit test, because the secondary is short circuited. So, let us so to say so the secondary is short circuited. Now, again I should actually honestly connect a ammeter in the secondary. I have to measure the currents here. On the secondary side, I need to connect a ammeter. Now, the thing that I am going to do is adjust this primary voltage source VSC such that full load, that is the rated current, in other words the rated current flows through the secondary. Okay. The rated value of the current is going to flow through the secondary. I am going to adjust the voltage supply to this. So, how much should I usually require this VSC value? Maybe like 1/20th of the rated value. Suppose approximately let us say that 5% is the regulation value, that means I am expecting 5% drop. Now, this drop is happening because of what? Rated current into ZSC, so into the not the ZSC, the Z net, the leakage impedance of the transformer, which for the sake of discussion in today's class I am going to treat V 1 minus V 2 dash upon V 1 into 100 as going to use this as voltage regulation. So, that means voltage, what I am trying to tell you, there are two definitions of voltage regulation in practice in use. This is the more common one, but this has this is the numerator is always the voltage drop, and these are the magnitude drop in the magnitude of the voltage from primary to secondary, but normalized, you can normalize it on V 1 also, and you can normalize on V 2 dash also. If you by and large know that you are going to connect the rated supply only to the primary, then this definition is easier to help and do calculations, because this itself is a derived parameter. This definition leads to trickier formulas. So, under the assumption that mostly we will be connecting our primary side to the supply voltage, I can derive elegant formulas using this definition. So, this is the definition that I am going to use today. And so V dash, you know, V 2 referred to the primary side is what is known as V 2 dash. So, because the leakage reactance is a small value, right, if the leakage reactance becomes larger and larger, the voltage regulation under normal operating conditions will become 0. Now, you may say, okay, why not design a transformer whose leakage reactance is as close to 0 as possible? Resistance you cannot avoid, but I can actually take care of the leakage reactance part of it. This is actually leakage impedance, to be honest, and so I can reduce the leakage reactance by more making sure, you know, that magnetic material is much better, the leakage flux is much lower and all that kind of stuff. but that is not what usually is done, because even the person who buys, the utility, for example, a distribution company which buys this equipment, buys transformer, also specify a desirable value of leakage reactance stroke impedance. The reason for specifying this leakage value is that, see, if you have like 1% leakage reactance, assuming that the R is very negligible, then the leakage reactance only plays the predominant role, and you connect 1 per unit, which is 1 per unit means 100% rated voltage. Then what it means is the short circuit current could be as high as 200, it can be as high as 100 times. 100 times rated value. You will get to do these things in more detail in a power system course, but this 100 times large short circuit current may be detrimental to the device, and the device may be lost, damaged and lost. So, even under the short circuit condition, a transformer will experience significant amount of forces on its turns, its current is going to be very high, and the B and the I also interact, and there will be significant forces also acting on it, and heat will be generated. If the current becomes 100 times, then the copper loss will become 10 to the power 4. So, the heat risk of fire hazards, permanent failure of the transformer is there. So, usually one may want to restrict short circuit current, means bolted short circuit, there is no impedance coming in the short circuit. I mean, for example, suppose a tree falls on a conductor, then the tree resistance comes in the part of it. But suppose the wire itself falls to ground, then it is called a bolted fault, zero impedance in between the equipment and the ground. So, in such worse condition faults also, we want to restrict I short circuit value to maybe 8 to 10 times the rated current, and then there will be some protection equipment which will disconnect the supply. So, there will be some protection equipment which will disconnect the supply. So, all this means that the leakage reactance is deliberately not set to 0. Now, coming back to the test, this is why I just gave you a motivation why it is also a design parameter, but now coming back to the test, we are going to circulate, because we have connected the ammeter on the secondary side, we are going to circulate a rated current on the secondary side. When we circulate the rated current on the secondary side, we will not require rated voltage on the primary side. Rated voltage on the primary side will create, as I told you, 10 times approximately 10 times rated current. So, therefore, this will be like if you just want to send the rated current through the secondary side, this will be only requirement will be around only 1/10 of the rated voltage. So, therefore, the rated you need a, that is why I said you need a variable voltage supply. You adjust it its values so as to send full load, full rated current on the secondary side, and then measure this current, the wattage and the voltage which is applied. So, in this case the loss which is I rated primary times R1 plus R2 dash square, this is the copper loss or the PSC short circuit loss. So, this is the loss which is going in the transformer, and because you know V by I, so you get the value of R1 plus R2 dash plus square plus x1 plus x2 dash square under root, and this current being known on the primary side, this already being measured by the wattmeter. You know this particular value, you know this ratio also, you have measured it, you know this. So, you can calculate x1 plus x2 dash. So, you cannot segregate R1 and x1, x1 and x2 dash, but you can get this net value. So, using this circuit, essentially you are able to get this approximate equivalent circuit of this equivalent circuit of transformer. This much equivalent circuit transformer you are able to get, and you are also able to get efficiency of the transformer. For example, suppose it is connected to rated load, okay, at power factor cos phi. Then what it means is, rated load means full load volt ampere. So, then your output is going to be full load, it is going to be full load volt ampere into power factor, and the input is going to be full load, this is in watts, right, this is in watts into power factor, this is the voltage, plus because full load current is flowing. So, whatever is the short circuit losses that you measured, that PSC, and whatever are the iron losses which you have measured as POC into 100 will become the efficiency of the transformer, percentage efficiency of the transformer. And now suppose you say I am running it at only 50% of the, if you say that I am running it at only 50% load or 75% loading condition, which means the volt amperes that it is drawing is only half of the rated value or 75% of the rated value, that is 0.75 times the rated value. Then if you want to know the efficiency there, then again the numerator which is output in this particular case will be, so I will call it as, suppose it is running at x times the rated value. So, x into full load volt amperes into power factor divided by the output, which is again this full load volt ampere into power factor. Now, if the current becomes half, what happens to I square R losses? It becomes 1/4 of the rated value. So, therefore, the I square losses will become x square PSC, and the open circuit losses, which are the core losses, they will not change because the voltage which is connected to the supply is still 100% voltage only. So, therefore, this will become, I am sorry, this should be x, this will become the efficiency of the transformer under efficiency of the transformer when it is working at some another loading level and power factor from what is at the rated condition. Okay. Now, the last thing that we need to discuss is the regulation. Approximate value is what I am interested in calculating. I am trying to give you basically simple formulas. So, for that purpose, this definition, this this simple equivalent circuit suffices. So you have, if you draw the equivalent circuit now, you have V 2 dash. I am going to start from here V 2 dash and add this drop, voltage drop, and get the V 1. So, let us say the current is V 2 dash. So I 2 dash, and this is my load power factor phi. So, I draw a parallel line like this and take, let me change the color. So, I get some I 2 R 2 like this, and parallel in parallel, and so this is R net and this is, let us call it as X net. So, I will get this as I times, or I 2 dash, or I 1, whatever you want to write, I 1 times R net plus J X net. So, I draw I 1 into R net here, and then take for this J a 90-degree lead like this, and I write I net plus J X 2 here, and then I join these two finally, and I get this voltage drop, and which is happening inside the transformer, and I get this as V 1. So, if as an approximation, this one and this angle, let me for the time being call this angle as phi SC, short circuit angle, this phi SC. Why do I call this as phi SC? Because in the short circuit test, VSC is the voltage which I have applied, VSC is the voltage which I have applied into this rated current ISC into, so let, in other words, PSC is VSC ISC cos of phi SC, is it not? And the current lags the voltage. What is the voltage which is applied? This is VSC. This is the voltage in the short circuit test rated rated current is made to flow. So, I 1 is the rated current, the rated current is up is so the V 2 dash is just I mean to say this is V s c, this is the I s c, the rated current, and this is the phi s c, because why is that? Because this voltage is 0, this voltage V 2 dash is 0. So, the only basically your circuit is R 1 x 1 dash x net, R net, J x net, V s c and a short circuit. So, V s c divided by, if you look at the current I s c, how much is it lagging V s c according to this particular value. Hence, this is the equivalent circuit. So, therefore, this V s c is equal to I rated into Z leakage whatever is there. This is the magnitude, which is the I which is here, which is exactly here. The V rate, the I rated is flowing in this. This is I rated, and this is I rated times the Z. So, therefore, this is V s c, and this angle phi s c is shown here, and this angle here is phi. So, therefore, if I so to say expand it here, then this angle here is phi s c minus the phi load, this is the angle, and so this vertical intercept is going to be equal to V s c into sine of whatever, and the horizontal intercept is going to be equal to, which is the horizontal intercept that I am looking at, this one. This horizontal intercept is going to be equal to V s c into cos of phi s c minus phi. So, if this is, as you can see from this picture also, this is not a dominant part, this is the dominant part, V 2 dash is the dominant part, this is a small, much smaller than what I have shown in the figure, not comparable. So, this will not make much difference, only this will make significant difference in bringing this summation, this square plus this square is equal to V 1 square, but because this is much smaller percentage, this square is much smaller percentage of this square. So, as an approximation, we can write V 2 dash we can write V 2 dash to be approximately equal to, I am sorry, we can write V 1 to be approximately equal to V 2 dash plus V s c into cos of phi s c minus phi 2 or phi 2 minus phi s c, whichever way you want to write it, and therefore, V 1 minus V 2 dash by V 1 is going to be equal to V s c by V 1 into cos of phi s c minus phi 2, which is the regulation in per unit, and if you multiply it by 100, it will give you percentage regulation. So, therefore, per unit regulation is V s c divided by V 1 into cos of phi s c minus phi 2, and percentage regulation is going to be equal to V s c by V 1 into cos of phi s c minus phi 2 into 100%. So, this is a this is a these are the basic uh, tools which we have got to evaluate the performance of the transformer. Let us take a problem and solve using that. Okay. So, following tests were obtained on a 50 kVA transformer. Primary voltage is 3300 volts, secondary voltage is 400 volts, primary power is um, 400 watts. So, let me do some annotations here itself. This is POC, this is V2, this is V1. So, immediately you can see that if I take 3300 by 400, that is 33:4, that becomes the N1 by N2. Then this opens whatever, since the primary voltage is applied, whatever is measured is the rated open circuit loss or the iron loss or the magnetic core loss in the transformer. Now, short circuit test. Primary voltage 125 amperes, primary current is 15 amperes, primary power is 600 watts when secondary at full load value. So, because you have connected the secondary current, you have set it to full load value, you have to apply a much smaller fraction of the primary voltage to get, because there is no load, the current is not to be pushed through the impedance of the load, it just short circuited there. So, only the current has to be pushed through the leakage impedance, and to get a rated value of the current pushed only through a small leakage impedance, a much smaller voltage is required. So, therefore, the primary voltage which is required is fraction of 3300, only 125 by 3300 is the fraction that is required, and the current which is measured from the primary side at that time, this is also therefore the full load value of the current from the current also at the seen at the primary side, and you get the PSC here, full load power system PSC here. So, now calculate the efficiencies at full load and half load for power factor at 0.8. So, we will stop here now, and we will do the problem solving in the next class.